with the last speaker of the morning and of the symposium on temporal existence. Sattig, please say it.
So now, thank you, Christian. Really thank you for the invitation. Okay. What is the nature of the passage of time? That's my question. So, okay. So, what is the nature of the passage of time? That's the question. In the first part, I will give an initial characterization of the phenomenon of passage that I'm interested in. The plan there is to give a characterization that is familiar but obscure. And in the second part, I will distinguish between two broad, high-level approaches to explaining this phenomenon. One is the standard one. We'll briefly characterize it, put it aside, and look at the other one. Then in the third part, I will sketch a particular implementation of this approach. There are other implementations I want to look at. I will sketch an implementation that I think is the simplest one, and that's where the notion of a system of relativization will appear. So let's begin. A phenomenon of passage I will look at. Passage is sometimes used in different ways. Doesn't matter. We will just look at the following two cases. Look at the cases, the visual cases, and let me compare them to isolate the aspect that I'm interested in. So here's the first case. That was the first case. Here's the second case. So let's compare them. In the first case and in the second case, we can talk about two objects, a cube and a sphere. We can also talk about two shape states, a cubical state and a spherical state. I don't care. For you, this might matter. For me, it doesn't. So I'm just going to talk about objects, but this is out of the way. In the temporal case, we have an object confined to one moment, a cube, and we have another object, a sphere, confined to another moment. In the other case, this one, the second case, we have a cube confined to one place, one region, and a sphere, another object, confined to another region. So that's a similarity. Another similarity. In the temporal case, the cube and the sphere are distributed by being temporally apart by a certain amount of time. In the spatial case, the cube and the sphere are distributed by being apart by a certain amount of space. So intuitively, that's another similarity. So here's another one. In the temporal case, the cube is there before the sphere, not the other way around. So there's an order. Now let's be really naive about space and say, it's similar here. The cube is not just next to the sphere, which is symmetrical, it's also to the left of the sphere. So there's even, intuitively speaking, there's even an order in space. So these are all similarities. Yet these two cases appear intuitively extremely different. So let's focus on the difference between them. Let me put it this way. And again, the aim here is that it's familiar but obscure. So in the temporal case, it seems, let me start with the spatial case. In the spatial case, it seems that the cube and the sphere are somehow there together. They seem to coexist, right? They seem to be there in concert. But in the temporal case, it's not so. The temporal case, the cube is there, but it seems to disappear as the sphere appears. It seems to vanish as the sphere emerges. So they're not there together in some sense.
Can I see the first case again? Just
Yeah, to remind you.
I forgot what it was.
So here, this is the cube. Right, it's gone. The cube's gone. Can we agree on that?
Yeah.
Okay. This, by many people here, this is often put in terms of the temporal case being dynamic and the spatial case being static. And this is the phenomenon, that difference between the spatial case and the temporal case. That is what we're going to talk about here when I talk about passage. What is the nature of the difference? What is it about? You can take it as brute, but what is it about? You might think that's hopeless. No, let's wait. Let's try to explore this. And I'm going to put something in front of you for your consideration. I'm not saying that's the right way. I want to understand what this difference amounts to. Two approaches, two high-level approaches. They're still not really precise, but they're two different ideas. So the first idea, which is the standard idea, and everyone in this room knows this, is to try to decode this difference, understand it in terms of the concepts of past, present, and future. And so Kurt Callender talks about the tripartite division of time into past, present, and future. I like the term, so I use it, and I'm calling this the tripartite approach to passage. So here is as I announced, a quick sketch, which I'm going to give you and then set as aside as my contrast case. So intuitively, when you look at the case, it's clear that passage, at our phenomenon, it's clear that passage requires temporal order or temporal direction. It's perfectly clear that intuitively, when the cube disappears as the sphere appears, there's a certain order presupposed. It's not the other way. It's not that the sphere disappears, the cube appears. No, it's the other way around. So there's definitely order. It's perfectly clear that passage requires temporal order, but it's also quite plausible that that's not enough. A temporal order is part of passage, but then you have to add something. Something else needs to be there for this to be passage in the temporal case. And the way it's often put is, well, the spatial case intuitively described in terms of left and right, that has an order but doesn't have passage. And even if we don't do it in terms of left and right, we can imagine a space that is directed. It's not going to have passage. So what we can put the challenge in such a way, you want to understand what needs to be added to temporal order to get passage. And the standard view is what needs to be added is tripartite change. It's my label for change with respect to past, present, and future, which characterizes the dynamic case, but not the spatial one. So here on the standard approach, they seem to be there together. They seem to coexist. This is the intuition is cashed out as they're co-present. They're both present. And in the other case, they're not co-present because, right, this is the case, as the cube is present, the sphere is future, but then the sphere moves into the present and pushes the cube out into the past. So there's change with respect to which object or which shape state is past, present, and future. That's the standard approach. Everybody knows this. And now I'm going to try to go another way. And the plan is to give an account of this phenomenon that has nothing to do with past, present, and future, but it is still illuminating and reasonably clear and simple. So that's the task, right? And I'm going to begin with a similarly high-level description of the idea. So let's go back quickly to the spatial arrangement. And here's how I want to get you, just set you on the track that I want to pursue. So take these two objects. They form a spatial arrangement. So on the standard view, the thought is there is a certain structure or a certain property that this case lacks, but the temporal case has. So the temporal case is such that it instantiates tripartite change, and that is absent from the spatial case because they're just co-present. So in the standard view, passage cash out in terms of property or some structure that the spatial case lacks, the temporal case has. So I want to turn this around and think of an approach on which passage consists in a property is a structure, whatever you want to talk about, whichever way you want to talk at this stage, that is absent in the spatial case, but so that is present in the spatial case, but absent in the temporal case. Exactly the other way around. So there's some structure that is there in the spatial case that is not there in the temporal case, and that's what makes the difference. So what might that property be that is absent in the spatial case? Sorry, that is present, that is there in this case, but not there in the temporal case. And the suggestion is, broadly speaking, it's geometrical. It has nothing to do with past, present, future. It has something to do with a geometry. Okay, so here's how I want to introduce this idea. Fix on any point on the surface of the cube. Fix on any point on the surface of the sphere. Try to imagine that a line is drawn to connect, or the drawn line connects the 2 points. No problem, right? You can do this for any points on the sphere. That are facing towards you. Now try to do that in the temporal case. So fix on any point of the surface and try to imagine that it be connected by a line to the temporal case. Of course, you can't do it. I say, yeah, because as the sphere appears, the cube is gone, so you can't connect them by a line. You can't connect them in a geometrical sense. So that's the heart of the idea. The thought is, what passage really comes down to in the temporal case is that while in the spatial case, the cube and the sphere are geometrically related, they're geometrically connected. In the temporal case, the cube and the sphere are geometrically isolated. That's the thought. So the proposal is that on what I'm going to call the geometrical towards the passage, that temporal passage is temporal order in combination with this, at this stage, very high level description of geometrical isolation.
Sorry, but this is a picture of the way you presented stuff in your
Wait. Again, as in the previous talk, it's going to be answered at the end of it. And then you can tell me whether. So, there are different implementations of this idea that passage is temporal order plus geometrical isolation. That's important. So I'm by no means now claiming that what's coming up next in the third part of the talk is the only way. Of course not, but it is, as from where I stand at the moment, the simplest. To get there, I need some conceptual tools, and I will introduce them as we go along. And the first concept is that of a system of location, and that is meant to capture something very, very familiar, standard, very intuitive conception of three-dimensional space as a system of location. So it's really just a way of framing in an explicit way what we usually work with anyway. So here is the starting assumption. So I'm going to apply these concepts to time in a moment. We'll start with 3D space. So a standard assumption of 3D space is a system with a certain intrinsic geometrical structure, and just very briefly the points of space. So space has points. They're connected to each other by line segments, which I will just call paths in what follows, and a measure of the length. The shortest path between any 2 points, P1 and P2, is the distance between. So that's what I will assume, and this concerns the intrinsic geometrical structure of 3D space. Now I want to ask, first of all, I want to characterize intuitively what we expect this three-dimensional space to do, what its function is with respect to the inhabitants of space, which I will just sometimes call the domain. So the thought is, again, intuitively, that 3D space has certain extrinsic organizational functions. the space it doesn't exist and in love with its own geometrical intrinsic structure. No, it's there to do something. And intuitively, the inhabitants of space are distributed across space with certain amounts of space. Intuitively, these are the metric notion, of course, from a 3D space, so no need to bring an order here. And so here's an instance, an object A and B. They're separated by 10 centimeters, so the space is there to give us that. Right? A and B are material things or states, whatever, and they have a certain metric distribution. Of course, the 3D space is there to impose that on its domain. But now I want to ask, so how does it do that? So first of all, they have to be embedded in space. So now we're talking about something like spatial existence, right? So how are they in space before they even can be ordered? How's the domain in space? And well, standard view, well, it's located in space. So the spatial being is, well, just be located. And I mean exact. In what follows, I mean exact location, but I'm not going to be very careful about this distinction. So how now, given that it is in space but being located there, how does the space, given its intrinsic geometrical structure, perform its organizational function? By location. And here's the slogan: the system's geometrical structure. The intrinsic one is attributed to the system's inhabitants by location. So here's an example. Right, the example is A and B are separated by 2 centimeters. Now, what we want to get is this intuitive notion of a metric spatial distribution of the domain, the inhabitants of space. They're intuitively distributed across space by certain amounts of space. So how do we get that, given that 3D space has a certain intrinsic geometrical structure? Here's an application. The basic thought is that things are distributed in locational space by standing in relations of spatial distance to each other. And they inherit these spatial distance relations from their location. So here's the example applied to the figure on the right. You can, if I point, you can see that's, yeah, right. So here's the space itself with its intrinsic structure, right? So there's a path between these points P21, and the measure is the distance. I'm packing this into the pink line. Now, A and B are material objects, and A is exactly located at P1. B is exactly located at P2, and they're only there. And since P1 has distance of 10 centimeters to P2, X and Y have that distance. But not only that, X also stands in literally that path. So that line segment literally now obtains between the two objects. So the idea of a system of location is that the intrinsic geometrical and metrical structure is transferred to its content by location. That is what exact location is for. That is its function. That's how I understand it. So it's a transfer of intrinsic structures in this establishment of an isomorphism with the intrinsic structure and the content. So that's the basic idea of what a system of location is in terms of what, not just what its intrinsic structure is, but what it does to the content. So time can be understood in an analogous way, just straightforwardly analogous. This is not where I want to be in the end, but this is the kind of locational conception of time that many here have used in the background of discussions of multi-location, unique location. So I'm just going to go quite quickly in just applying these ideas, system of location, that we introduced in the familiar case of 3D space to time. You know exactly how it works if you understand the first thing. It's going to be very easy. We can do this very quickly because we just basically rewrite everything in terms of moments. So time's a system with a certain intrinsic geometrical structure. Of course, it's one-dimensional. That's much simpler. The points or moments of time are connected by line segments or paths. I'm going to call them paths again. A measure of the length of the shortest path, geodesic between T1 and T2, is the distance between the two moments. So that's just straightforward intrinsic geometrical, so metric and metric geometrical structure of the time, which will be in the background. Now, we ask analysis of spatial cases. First, what we observe, and then you ask how the system accomplishes that. We observe that time has certain extrinsic organizational functions. Of course, one of the functions is to order its domain. Another is to spread it out metrically, to distribute metrically. So intuitively, the inhabitants of time are distributed across time by certain amounts. Example, A exists and B exists in separation by 2 seconds. This is supposed to be a really neutral, semi-intuitive way of putting metric fact. Okay, now the third question, Alexi. So how do they work together? So what's the role of the system's intrinsic geometrical structure for its organizational functions? And assuming or considering time as a system of location, that works by location. So the system's geometrical structure is attributed to the system's inhabitants by location. Here's an example, it's analogous to the spatial case. A exists and B exists in separation by 2 seconds. So how does that work? Well, we basically flipped the earlier figure upward. And then we have a temporal system of location in application to this case. Things are distributed in locational time by standing in relations of temporal distance to each other, and they inherit these from their locations. So that means moments of time, well, they're connected intrinsically by these line segments, by the paths. And that structure, if you just look at this example, T1 and T2, is attributed to the contents by location, in the sense that if we have A located exactly and uniquely at T1 and B at T2, then since T1 has a distance, the little geometrical distance of 2 seconds to T2, A has that, literally has that distance to B. So it literally stands in that, is really connected by this line segment that has a length of 2 seconds. So all of that is familiar. Now, this is my basis for introducing a different notion. And now you will see, as it turns out to me, there will be some convergence with Kit's picture. But of course, I'm coming from a very different direction, but I think convergence is good. So I think that's a good thing, right? I hope you think so too. Okay. Now, we think of time in a way that starts exactly the same way that we're now familiar with, namely with time as a one-dimensional system with a certain intrinsic geometrical structure. That's a good idea because it's a clear account of what distance is. We got this under control. We have many people here who tell us exactly what that amounts to. So the points or moments of time are connected to each other by these paths, and the measure of the shortest path is the distance between them. So all that is familiar. The second point is again the observation that time has certain extrinsic organizational functions to sequence, to distribute. Okay, same example as before. A exists and B exists in separation by 2 seconds. Now, when time is a system of location for A and B, to have any separation, they must exist temporally. They must have temporal existence. In the case of a system of location, this intuitive notion of temporal existence gets cashed out in terms of location. This literally existing at a time is being exactly located at a time. So on this system, nothing is located at the moment. So temporal existence does not get understood in terms of location. In fact, nothing is even related to time. Literally stands in any relation to time. So how are things embedded in time? How are they ordered in time? and how are they metrically distributed in time gets a completely different account. So I'm going to start with a slogan and then illustrate it, and then I'm going to apply it to passage. Okay, so the question is, so what is the role of the system's intrinsic geometrical structure for its organizational function? First of all, just clearly contrast to how that works, how here with how it works in the system of location. The system's geometrical structure is not attributed to the system's inhabitant. Again, its geometrical links, its geometrical structure is not at all transferred to the contents. The system works, it acts in a different way. It acts, and here comes my only primitive, it acts on its inhabitants by relativizing the attribution of properties to its inhabitants. So it does not take its intrinsic structure and impose that onto its domain. It's rather that, here's my slogan, the system's geometrical structure acts purely as an envelope of attribution of non-geometrical properties to the inhabitants. So the intrinsic structure guides the description of how the system is temporally ordered and how the objects are metrically distributed, but then do not literally get to stand in any geometrical relations. So here's our example with the new account of how that works. So the denizens of time intuitively are distributed across time by certain amounts of time. So A exists and B exists in separation by 2 seconds. So here's how this works in the system of relativization. Things are distributed in the system by existing relative to moments, by existing at moments. And these moments stand in relations of temporal distance to each other. That's it. So A exists and B exists in separation by 2 seconds is our case, because, and here's the account, A exists relative to T1, B exists relative to T2, and T1 has a distance of 2 seconds to T2. So given that T1 and T2 are connected, the points in time itself are connected by a certain path with a certain measure, what you need to do, in fact, all you need to do to give the content of time, the inhabitants, the denizens of time, an order and a metric distribution is to determine relative to which moments they exist. So no geometrical relations are attributed to A and B directly. They play an indirect role. So the structure guides the description of the content without making it into the intrinsic fabric of the contents. That's, if you like, the technical idea. And the result of this account is that you get the contents ordered and metrically distributed. So you get a metric, you get an order, but you don't get the geometry with it. You don't get geometrical relations. That realizes, that's an implementation, a realization of the idea that A, which is confined to T1 by existing relative to T1, and B, which is confined to 2 by existing relative to T2, are geometrically isolated. They are ordered in time. They are apart by an amount of time, but literally do not stand in the relation, a measure of which is the distance. So they do not have a path connecting them. This is now something that holds not just for A and B, but for all of space, all of 3D space, to give us, this will yield a very, of course, a simple separation of 3D space and 1D time, where we understand that everything that goes on in 3D locational space, so pink means this stuff is geometrically connected. Right? Everything that goes on in 3D locational space goes on relative to moments in relativizational time. So everything in 3D space is geometrically integrated. what goes on in space relative to one moment, goes on in space relative to another moment, gets temporally ordered and gets temporally metrically distributed, but not literally geometrically connected in analogy with how things are in space. So that is the foundation, and now I'm going to apply that to passage to the initial case to give us an implementation of the geometrical approach. Everything I have to say about this is contained in this figure. So just look at the bottom half. Here you have the spatial case. I changed the cancel around a little bit. We have our cube, and we have another geometrical object. And of course, they are geometrically connected relative to T1. Relativization here. All of space, and all inhabitants, all its locational inhabitants are relativized to the moment. So they are geometrically connected relative to T1. So our intuition is satisfied that they're there together, that they coexist. Where, remember, I'm going for a proposal where the coexistence intuition is ultimately geometrical. So look, now same goes for space relative to T2, but now compare them, so T1 to T2, compare them across time, look at them across time. They are, all of that is embedded by relativization and system of relativization. So the cube and the sphere are not geometrically connected to each other. They're geometrically isolated. There is no spatial relation between the cube and the sphere because they're confined to different moments. Remember that. And the spatial relation, the spatial distance relation, only obtains relative to a moment. As far as the domain is concerned. And there are no cross-temporal geometrical relations, so they're geometrically isolated. So in a time is conceived of as a system of location, then the natural picture is, of course, to add time, even 3D space, as a fourth geometrical dimension. Time is just another geometrical dimension, and the four-dimensional system is just a four-dimensional system of location, where our familiar geometrical objects and their shapes are embedded by location, and they, by virtue of being embedded by location, inherit geometrical structure from the four-dimensional system. And in the four-dimensional system, distance relations stretch across 4 dimensions. So if time is conceived of as a system of location, the pictures can be very different, because then what happens exists at one time will exist at another time will intuitively add up geometrically. There will be one 4-dimensional geometrically interconnected arrangement, but not here. Here, the geometrical arrangements only hold across space, but not across time. So our intuition that in the tempo case, the cube seems to disappear as the sphere appears, it's gone as the sphere appears, I suggest, comes down to this. First there's the cube and then the sphere. The cube exists relative to T1, only relative to T1. The sphere exists relative to T2, and only that. Since T1 is earlier than T2, they're ordered. But that's not all. We saw that temporal order is not sufficient for passage. So the intuition that these are ordered, but there's something else. One's gone from the other. One's gone as the other appeared. We can't imagine. Remember that we can't imagine a line drawn between them. That's the heart of the passage intuition. Here it's cashed out quite simply following way. In time understood as a system of relativization, there are no cross-temporal, none whatsoever, cross-temporal geometric relations in the domain. They are, of course, in the system itself intrinsically, but they're not transferred to the domain. That's why it seems that one's gone as the other appears. They're not there together. Ultimately, a geometrical intuition. That's the idea. How much time do I have left?
So you have, if you want, another 10 minutes.
So this is just a conception of passage, in the sense that it is an attempt to start with something really familiar, pervasive, and to unpack it in such a way that we're not introducing, as often done, we're not introducing another primitive concept and then announce, well, by the way, that's passage. The proposal is that there's an account of that dynamicity intuition that comes from a specification of an entire system in which things get a certain metric distribution and order. So the passage comes from the makeup and the function of the system, but it is just a conception of passage. So I'm sure everyone who's now wondering, so what am I supposed to do with that? Is that supposed to be how the world is, or what? So there's a question now, which I now have 8 minutes, so I'm going to use them for that. Is the question of whether that conception, first of all, how it relates to space-time conceptions, foundations of physics. And then there's the question, on the other hand, how it relates to the experience of space and time, human perception. I'm interested in both of these. Both of these questions are work. Not only are they individually work, relating them is also work. I can't do this work here. I have 6 minutes. I can't do it. So I'm just gonna, because you're gonna ask me anyway, I'm gonna just say what view I'm working with. I'm just gonna say where goes what, right? So and this is where, so this is the end of the convergence with Kit, because I'm not confident enough. Chris is here, and Tim's here, and Dan is here, to say anything that radical about space-time. So space, the simplest and most natural and conservative view of space-time is as a 4-dimensional system of location. That, and I'm just not confident enough to try the system of relativization in application. Right? Oliver can do this, I'm sure. I can't do it. So this seems to be the conservative view that space-time is a system of location, and then there's no passage of that sort in the objective world. And then this is what I'm working with. So what's the point of this? The point is that I'm seriously entertaining the idea that time is experienced as, or its structure as given in the content of perceptual experience, as a system of relativity. Space as a system of location, 3-dimensional system of location. And time is given to us in all of our experience, all of our temporal experience as a system of relativity. So that passage really only enters our lives at the level of the content of perceptual experience. And this is an attempt to give a very simple account of how to fit it in there. But it's not only that. Last word. I have something else. I want to be able to connect the two, in the sense that I want to be able to explain under what conditions and why, in a sense, why the human brain reinvents time. If it's situated in a 4-dimensional system of location, why does it represent time and space so differently in perception? And this account is supposed to give us the conceptual foundation for assessing this properly. And my hypothesis is that a system of relativization, in a way, extracting the metric time, but leaving the geometry behind, much simpler. And this simplicity counts in view of the computational resources of the brain. So the hypothesis is that we are experiencing times passing in this sense, because the human brain is not able or lacks the sufficient resources to represent 4D spacetime even for short intervals. So it simplifies. The passage is a result of. I'm done.